So let's get going. All right, let's get cracking. So we ended at the nitration of benzene, and now we're here, right? So like, pause here. What we spoke about before is that the main mechanism for reactions of arenes is electrophilic substitution, right? And we looked at the electrophilic substitution there, right? So I'm gonna have to put in the description of the two YouTube videos I put on the nitration and the bromination. 'Cause I think I put addition, right? That's wrong. I have to change it to substitution, right? So let me actually join on my phone so I can let the persons in. Okay, so in electrophilic substitutions of arenes, a hydrogen atom in the ring is replaced by bromine or a nitronium ion, right, or another suitable group. So we looked at that briefly. Hopefully, we could remember all of that. Right, electrophilic reagents in bromination of benzene is polarized, right, by a bromine molecule. Right, so we could look at that as well. When benzene is brominated, a halogen carrier is required, and that is what we call our Friedel-Crafts catalyst, right? Which, in the case that we use, the example that we use was Fe3, right? Fe3 bromide. That's what we used. Okay. And then when benzene is nitrated, right, the nitronium ion is our electrophilic reagent, right? Can anybody remind me at what temperature does the nitration of benzene occur the best? I gave a temperature yesterday. What temperature is it? Does anybody remember? Well, it's not. It can happen at 10 degrees, but the temperature I gave was 55 degrees, right? That's the temperature that I gave, right? So at glacial temperatures, happens really slowly. We're gonna have it at around this temperature. It should be fine here, right? We're gonna look at glacial temperatures and which reaction of arenes we use at below 5 degrees Celsius and stuff like that. But yeah, and we also use it in the presence of sulfuric acid. It tends to act as or stabilizing agent for our nitronium ion. That's what the sulfuric acid is for, right? And it can, I guess, act as a catalyst more or less, but it's usually to stabilize the nitronium ion. And we're gonna look at that. Okay, so let's have some fun. Benzene reacts with a mixture of concentrated nitric acid and concentrated sulfuric acid to produce nitrobenzene. I know, right? Revolutionary. Write an equation to show the reaction between nitric acid and sulfuric acid for 2 marks. Then describe the reaction mechanism for nitrobenzene for the nitration of benzene for 14 marks. And then the next question asks you to describe the mechanism for the halogenation of benzene with bromine in the presence of a Friedel-Crafts catalyst for 14 marks. Do you guys think you'll be able to do this? Who thinks they will be able to do this?
Ah, sir. Not right now.
Now, not right now. Okay, no problem. All right. So I want you guys
Because
to take down this question. Go ahead. Say what you're saying. Say what you're saying.
is this like the stuff y'all did in the last class? Because I block out. Well,
Yeah,
there's like
this
a
is
thing. So
this is all that we did last time. So this is literally everything that we did yesterday. All right. So it's
oh
just
well, yeah.
asking you to do it. All right. Hopefully you don't black out this time because we're gonna be going into more and more complex mechanisms. All right. So just take the question down. I want you guys to try it. All right. So just try it and let me know the answers. All right. I'm gonna be sending the PowerPoint in the WhatsApp group. No. Well, not now, but after class, everything should be fine. But we're moving on now to methylbenzene, derivatives of benzene. Methylbenzene is simply benzene with a methyl group, right? So, who's that molecule? I want you guys to name that. What's the name of that molecule?
Didn't you just say it?
Didn't I say what?
You say methylbenzene.
Okay, so it's methylbenzene. All right, so I did just say it, but just make sure that you guys were following. All right, methylbenzene. Lovely. All right, so let's have a go at this. Name that molecule. Who's that Pokemon? Just name the molecule. Don't be shy now. Come on, guys. I know you can do it. I know you have it in you.
And what's the question?
Look on your screen and name that compound. Name that molecule.
Isn't it metro? Hold on, wait. Isn't it methyl nitrobenzene or something like that?
Crazy stuff. All right. Interesting. That's an interesting approach at the name of this molecule. Any other takers? Any other takers? Come on, guys. It's all about interactivity. What's the name of this?
Um, one methyl two nitrobenzene.
Oh, no, 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 no. You don't have to do that, right? So remember what we're talking about is methylbenzene, right? Or what we call toluene. So this is toluene or methylbenzene, right? So what I'm trying to get to you guys know is that methylbenzene or toluene is a natural derivative of benzene. It is something that takes priority over all else, right? So what we're saying is that this is our base molecule. Think of toluene as our base molecule, right? This is our base molecule. So what we're doing now is adding a nitronium ion to our base molecule. So this is now what we call O nitrotoluene or what we call 2-nitrotoluene, right? Or we can call it nitro 2-nitromethylbenzene. You can see it? Can you guys see it? Carbon 1, carbon
Oh
2,
yes, yes.
2-nitro methyl benzene. Lovely, right? And it is at the O position. So it can be O, right? So because if it was over here, it would have still been 2 and it would have still been O, nitromethylbenzene, right? Or you can just say nitrotoluene, right? So 2-nitrotoluene, right? So toluene is our colloquial name, our regular name, and our IUPAC name is methylbenzene. Name this derivative. Go ahead.
Sir, four nitrobenzene.
No. Fix that. Fix the parent name. It's not benzene, but it
Oh,
is
sorry, yeah, four nitromethylbenzene.
lovely. Right? So one, two, three, four. Or we can call it P nitro. Right? So we can call it P nitro methylbenzene. Right? Or P nitrotoluene. Or you can call it just 4-nitrobenzene. Nitromethylbenzene. Right? So it is 4-nitromethylbenzene. Okay? Name this molecule.
Sir,
Go ahead.
for the nitrobenzene, do we always put nitro before the alkyl group?
Yeah,
Okay,
because the
thank you.
nitro is a substituent group that we look at.
Okay.
All right. So what's this? Name this.
Sir, one three dinitrobenzene.
1,3-dinitrobenzene. Lovely. All right. So it's fine. 1,3-dinitrobenzene is fine. Okay. So everybody can see why it's dinitrobenzene? I shouldn't ask that question. Sorry for insulting your intelligence. All right. You guys obviously see why. All right. So 1,3-dinitrobenzene. Lovely. So these are substituents that we're looking at, the substituents of benzene. So we're looking at toluene, right? We're looking at 2-nitrotoluene, we're looking at 4-nitrotoluene, and we're looking at dinitrobenzene, right? So these are some different substituents that we can look at, right? And we're going to be looking at them as we go through the rest of the slide, right? So let's have a look now. What we're supposed to learn? What we learn, all right? We must describe the nitration of and bromination of methylbenzene and nitrobenzene. We must explain the steps involved in the mechanism of nitration and bromination of methylbenzene and nitrobenzene. And we must be able to describe the reaction of nitrobenzene with tin in concentrated hydrochloric acid. Got that? We got that. These are the three things that we need to know. You see, everything else, we couldn't care less, right? So these are the three things that we need to know. Right? We need to know the nitration and bromination of methylbenzene and nitrobenzene. We need to know the mechanisms for both of them, and we need to know the reaction of tin and concentrated hydrochloric acid with nitrobenzene, and that is what we call the reduction. The reduction of nitrobenzene, right? And we know it's a reduction because we see tin, and tin is a reducing agent. So we know that already, right? Unit 1 chemistry done a long time, right? So we have no problem with that. So let's have a look now, right? Let's look at the hyperconjugation of toluene. We looked at this a little bit when with benzene, looking at the fact that you have different derivatives, right? So looking at the hyperconjugation of toluene, or what we call methylbenzene, we can see that the ring system specifically, right, is stabilized by the movement of electrons, right? So the movement of electrons around the ring per se in order to, right, to stabilize all the charges, right? So but methylbenzene can exist in any of these four forms, and what we can talk about within electron placement is that it kind of exists as all of these forms at the same time. But when we move up to, well, if you guys move to higher chemistry, we're going to be talking about wave particle duality and explaining through physical chemistry, right, how it actually looks. But in this case, we're just saying that, it can exist in these four different places at the same time, or it can exist in these four different um, hyperconjugations at different points within a reaction mixture, right? And what we can see here is that electrons are being donated to the ring, right? So electrons are being donated from the hydrogen here to the ring specifically, right? And that makes the methyl group what we call an electron donating group. This is important to the reactions of these compounds, right? So it's an electron donor, right? It's an electron donating group, or it's called a ring stabilizing group, right? So there are multiple different terms that we can use for it, and we're going to be using them as we go through the PowerPoint, right? Are there any questions or concerns before we move on? You see, I can't spell, so a 2N in a donor? Well, I do chemistry, I don't teach English. All right, so any questions? All right, everything seems fine. Moving on now, methylbenzene. So methylbenzene, right, tends to release electrons with the methyl group, sorry, tends to release electrons to the benzene ring, as I was saying, right? This reduces the positive charge on the intermediates formed and therefore stabilizes the intermediate. We were talking about benzene before on how if we change the hybridization of a carbon on benzene by adding an electrophile. And if I'm talking and you don't understand something, just let me know. Raise your hand and ask a question. All right? But otherwise, I'm going to talk as if we're understanding everything. Okay? So just stop me if you need to stop me. So as I was saying, right, the benzene ring itself will be destabilized by adding an electrophile to the ring and breaking sp2 hybridization. So we have hydrogen here. If we add an electrophile to the ring, this will make it sp3 stable hybridized and actually destabilize the ring, resulting in a positive charge, right? So benzene is like that. Benzene has no group on it. But with methylbenzene now, methylbenzene has a methyl group on it, and it tends to donate electrons to the ring. So it can stabilize the ring a little bit easier, right? So looking at this now, right, we have a positive inductive effect, right? Electrons are being donated to the ring, so it's easily stabilizes intermediates, right? So the possible intermediates formed are at the 2 and 4 positions, right? So they are at the ortho and para positions on the group, and that is why we call methyl groups ortho-para directors. We're gonna go through why they're called ortho-para directors, right? So the possible intermediates formed at the third position have a positive charge on other carbon atoms. We're gonna be discussing this. Okay? Let's bring our attention to this, right? When we go through the mechanism, I'm going to explain what I just said, right? Methylbenzene reacts with the same electrophiles as benzene, but is slightly more reactive than benzene. A mixture of isomers tend to be obtained, right? When methylbenzene is nitrated with a mixture of concentrated nitric acid, sulfuric acids, right? Well, and sulfuric acids rather. The isomers produced are methyl 2-nitrobenzene, methyl 3-nitrobenzene, and methyl 4-nitrobenzene. But because the methyl group is a ortho para director, right? It is a 2,4 director. It tends to create larger concentrations of the 2 isomer and the 4 isomer, and it tends not to create concentrations at the 3 isomer, right? Since mainly the 2 and 4 isomers are produced, we say that the CH group is in nitrobenzene is a 2,4 directing group, or what I would like to call an orthometa director, right? Let's have a look at that. Go ahead, ask the question.
Yes, sir. What do you mean by directing? Like when you say the group in nitrobenzene is 2,4 directing.
Okay, so let's have a look at this. All right, let me see if when I finish the slide, I'm gonna ask you if I answered the question. All right, so I'm not going to be looking at the mechanisms. We know the mechanisms already. You see, if you know the nitration of benzene and the halogenation of benzene, it's the same thing. So it's the same thing where the nitronium ion is created through the reaction of nitric acid and sulfuric acid, creating the nitronium ion, the electrophile, and then you add to the group and it breaks hybridization, right? It changes hybridization from sp2 to sp3 hybridization, and then the hydrogen leave to reform sulfuric acid. We talked about that already, right? So I'm not going to go over that. It's the same mechanism. What we now need to discuss is what is happening for the products, right? So what we're talking about on the ring, right, is that the methyl group itself is an ortho para director. What does this mean? Remember our ortho positions O, M positions meta, and our P position para. You guys remember when we went over that? So if you guys were here when I did that, right? So O, M positions, and this is the P position down here. Now, because of the destabilization, right, of the group when things are added to the meta position, right? Remember the slide here says no. The possible intermediates at the third position allows for a positive charge to exist on carbon atoms, right? So it means that, okay, let me actually slow down. Can anybody tell me what this means? What does this mean for the stability of the compound, right? When if a positive charge emerges, right, what does that mean for the stability of the compound? What are molecules trying to achieve? Let me ask that. As it relates to charge, what are we trying to achieve?
Stability, sir.
Stability. And what does stability refer to? Are we talking what are we talking about as it relates to charge and stability?
Like a neutral charge.
A neutral charge, right? So we're trying to gain a neutral charge, right? And if we don't have a neutral charge, we try to balance that charge by moving it, right? Through resonance systems. I asked you guys to review resonance systems because if you don't understand resonance systems, this is going to be a bit tough. So review that, right? So we try to stabilize the charge, right, through resonance, right? Or we try to dampen the charge by pushing electrons onto positive charges, right? But what we're saying is that when a substituent is added to the meta positions, these are the meta positions, it tends to be less stable. And we know that the less stable intermediates will not be produced, right? So look at this now. At the meta position, if we're nitrating toluene at the meta position, only 5% of the mixture will be meta. Only 5%, right? The methyl group specifically allows for the ortho and the para positions to be the most stable intermediates, to be the most stable products, right? Therefore, that is why we call it an ortho para projector or a 2,4 projector. Because when the groups come in, right, they either go to the ortho position or the para position. Question: you guys have seen runways, right, before already, right? Or whether or not you see it in movies, whatever it is, right? You guys know that typical guy that is on the runway with the two signs in his hand directing the plane to the runway? Those persons who direct planes with like the light up things in their hand, right? You can think of the methyl group like that. So when the nitronium ion is coming in, the methyl group is telling the nitronium ion to go to the ortho or the para position, right? So that is what it's doing. It's directing the nitronium ion. You're going either to the ortho position or you're going to the para position, right? But if you can risk it, you go to the meta position, right? But the methyl group does not direct groups to meta position. It is by chance that meta isomers are created, right? So that's how we see now that the ortho position, right, tends to be stable. We have 57% of our products being ortho isomers, right? We have 37% of our mixture being para isomers, but only 5 by chance being meta. So what we're saying is that the methyl group is an ortho para projecting group or a directing group because its products, right, the products with the highest stability are our ortho isomers and our para isomers. Questions? Any questions? All right. So nitration of toluene in the case of orthopara direction. For nitration of benzene, I'm reading from the slide. The product distribution is 50% ortho, 37% para, and only 5% methyl. In other words, the methyl group tends to direct the electrophile to the ortho and para positions. Right? Note now that the nitration of nitrobenzene requires concentrated sulfuric acid, and a temperature between 55 and 60 degrees Celsius, right? And that produces the electrophilic agent, right, which is our nitronium ion, which reacts with our methylbenzene. And since the methyl group is 2,4 directing, or what we call orthopara directing, right, it tends to release electrons to the ring and stabilize these intermediates, right? So what we're saying is that when we add nitronium ion to the 2 group, or the 4 group, right? The methyl group itself is able to release electrons to stabilize the intermediates, but it cannot do that when it's at the meta position. That's why it's so unlikely. All right. So me sitting here at chat enough. So do you guys understand what's happening? Are there questions? Do you understand what's happening? Okay, if there are any questions or concerns, let me know. If everybody's ready to move on, just drop a numeral 1 in the chat. Just drop a 1 in the chat, please. If everything is a little bit clearer. Shanique, do you have a question? Please ask a question if you don't understand. It's sinking in. Okay, it's taking a while. Okay. All right. So probably it's just one of those things that take a while to settle in. Right? So remember when we talked about all right. So remember when we talked about Markovnikov and anti-Markovnikov products? Who remembers that? All right. So what's the difference between Markovnikov and anti-Markovnikov products as it relates to stability? Isn't it that the Markovnikov product is more stable than the anti-Markovnikov product? That is why, right? The intermediates are more stable for the Markovnikov product. So it's similar to this, in which if we have a nitronium ion being added to the 2, right, position, then that is stable, right? It's added to the 4 position, then that is stable. But it's just simply unstable when it's added to the 3rd position. And that's why we call the methyl group a ortho-para directing group, because its most stable products are at the ortho and the para groups. That's why we call it a directing group. So when the nitronium ion is coming into the ring now, for toluene, they almost always go to the ortho or the para positions. That's why we call them ortho para directing group. It's like the methyl group is telling the nitronium ion to go either to ortho or to para. That is what I'm trying to get. So it makes a little bit more sense now, right? Because it's just think of it like that. The methyl group is telling it to go to ortho or para because we will be stabilized in that way. It won't encourage a meta addition or a meta substitution, right? Because that will be unstable. Okay? So hopefully that makes more sense. So if you
Sir,
go ahead.
can you go over again why the meta group would be unstable?
Okay. So I haven't gone in depth in it why it's not stable, right? But essentially, right, I just included this line, right, to just explain that. So the possible intermediates formed at the third position have a positive charge on other carbon atoms, right? So what we're saying is that the methyl group is able to stabilize at the ortho and at the para positions, right? But when you add something to the meta position, it is not able to stabilize as much, right? I'm not, I won't get into all of that because that might confuse you and it's not necessary for you to understand, right? But think of it like this, right? If something adds to the meta position, the methyl group is not able to stabilize that intermediate as much,
Okay, sir.
all right? So it's all about stability. There are only three things you have to know in organic chemistry, you know? Only three things. Where the electron them there? Is it going to be stable? Right? And what kind of attack? Three things and every organic chemistry reaction done. After you know those three things, you can look at something you've never seen before and you write the mechanism. Alright? Because that's all you need to do. Where the electrons are coming from. Is this stable? Right? And what kind of attack is going to be happening? Is it electrophilic? Is it nucleophilic? All right, something like that. All right, so let's have a look now. The bromination of methylbenzene is similar. All right, so let's look at this now. In the presence of a halogen carrier, FeBr3, the Friedel-Crafts catalyst, so it's necessary. The Friedel-Crafts catalyst is necessary with the methylbenzene as well, right? It reacts, right, as an electrophilic reagent, and then we have this now, right? We have 2,4 projection. Remember that the methyl group is always a 2,4 directing group, right? So we're gonna end up with something. Hold on, why can't I find it? Give me a moment, let me check something. I'm not finding it. Oh boy. All right, so it's not in the slide, right? We're gonna end up with something like this, right? So because of the rapid reactions of the halogens like that, we're gonna end up with this, right? So it's gonna be substituted until we end up with a compound like this. Can anybody name this compound, please? Somebody name that compound. This is just the first substitution. It's going to substitute until all the ortho and para positions are filled, right? So what is the name of that compound? Tribromo methyl tribromomethylbenzene. So it is 2,4,6 tribromomethylbenzene, right? That is the ultimate product of this reaction. There's a reason why I give you the ultimate product of this reaction because it shows up time and time and time again. It is not one, can't be one. Because remember the first carbon is on it has the methyl group there. So 1, 2, 3, 4, 5, 6. 2,4,6 tribromomethylbenzene. Lovely. All right, that is the ultimate product of this reaction. Okay, and as I said, I show you the ultimate product because it shows up time and time again. And this is a perfect display of the methyl group being ortho para directing because I've never seen a bromine on the meta group, right? The methyl group does not allow for the attachment of the bromine to a meta group, to the 3 or the 5 positions. No, no, no. Not stable. All right. So we have something like this. So everybody's fine with that? Moving on? Are ready to move on? Just drop a 1 in the chat if we're ready to move on. We already reached halfway through the hour. We know that we have phenols to look at and we have azo compounds to look at. So we can say, no, 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 no. Okay, so you can't say it's 2,4,6 directing. You can say it's 2,4 directing. Okay, so this is why I tend to use ortho para directing, because ortho covers the 2 and the 6 positions, and para is only the 4th position. That's why I use ortho para directing. Because what we're looking at, depending on what you're looking at, this is position 2 and this is position 2. So 2,4 directing. But this is why I use ortho para, because ortho para don't include 2, 4, and 6. Alright? So it's ortho para directing. Alright?
So the 6 would kind of be like repetitive.
Yeah, it would have been repetitive, yeah.
Okay.
Because it's repetitive and it doesn't apply to every situation. In this case, it can apply. But in a case where it's just one bromine, you can't say it's 2, 4, 6. Right? In this case, it's 2, right? Because you can only have it on in either 2 or whatever, right? But you don't have to get into all of that. But it doesn't apply neatly. Ortho para directing applies completely neatly to every situation whatsoever, right? But in this case, 2,4 directing. Okay, let's move on now. The nitrobenzene now. Nitrobenzene reacts with the same electrophiles as benzene. So once you understand benzene, you understand methylbenzene and nitrobenzene. All right, it is slightly less reactive than benzene. What is this saying? Let me give you all the information. We must look at every grain of information, right? We here say no. We look here. We look at the fact that methylbenzene is slightly more reactive than benzene. So what is happening now? Methylbenzene, CH3, is more reactive than benzene, which is more reactive than nitrobenzene. So you see when them come with the different questions talking about whatever reactivity of whatever, please note that. It is in the slide. Know every nugget of information, every grain. You must read everything. You must not only look at it, you must see the information. All right? Information is right there in front of you. So the 3 isomers, the ortho, meta, and para isomers are mainly obtained, right, for the nitration here, right? So, well, not for nitration, but nitration and halogenation. So, due to the production of the 3 isomers, the nitro group or the nitronium group in nitrobenzene is 3 directing. It is meta directing, right? It tends to withdraw electrons from the benzene ring through the negative inductive effect, right? This increases the charge on the intermediates formed, especially at the 2 and 4 positions. So, whereas the methyl group is orthopara directing, the nitrogen group or the nitrile group here, right? Well, not the nitrile group, the nitronium group rather, right, is actually metaport directing. So let me write it down. So where the methyl group directs to the ortho and the para positions, the nitronium group directs only to the meta position, right? So the nitration of nitrobenzene in case of meta direction. The meta is not always the minor product. However, in the nitration of nitrobenzene, the ortho and para are the minor products. Meta is a major product at 93%. 93% of the isomers obtained are meta. Right? So this says now that the nitro group tends to directly electrify to the meta position. In this case, it is meta directing. We can see that. Can we see that? Lovely. I'm just hoping that you stay with me, once you follow, once you follow, everything should be fine. Nahila, is everything fine? Joel, is everything fine? Gabriel, is everything fine? Is everything lovely? Nicholas, Ramona, Shanique, Victoria, is everything fine? Want to know, Talk to me if something isn't fine. Or this is nitration of. Wait, say, wait, question. What are you asking? Is there nitration of benzene? Of course. Of course. Let me go straight back to the slide. See it there? Nitration of benzene. It's the reaction there, it's everything there. It's the mechanism there. Yes, we have the nitration of benzene. Right? But look, we're looking now at the nitration of nitrobenzene. So we're adding yet another nitrile group to the nitrobenzene to give us dinitrobenzene. Right? So here we have two dinitrobenzene, we have three dinitrobenzene, and we have four dinitrobenzene. But we know that three dinitrobenzene is the most stable, right? Because it is three directing, or what we call meta directing. Right? Lovely. Okay, so let's move on. Okay, let's look at this now. So this is just what we're saying, right? So this is the most stable intermediate. Well, the most stable product, the meta, all right, because it's meta directing. Any questions? Questions or concerns? Ask questions now. Ask the questions now. Any questions? I don't bite, Any questions?
Sir, you can show um how the nitrobenzene would become the benzene, like the step by step process.
Okay, all right. So I can show it. Okay, so let's see. You want the step-by-step process, all right? Hopefully, okay. Hopefully, can you guys still my screen? Still see my screen? I mean,
It's
Yes,
there.
sir.
okay. Can you see it now?
Yep.
Oh my, you're still seeing it? Lovely. So I think the issue from last class gone. You can still see it?
Yes, sir.
All right. All right. So we're going to be moving a little bit swiftly, So if you don't follow, you might miss it, So I want to keep your eyes peeled and let's just go through this reaction because we do it already, So let's just go over it swiftly. Okay. So at the beginning we have step one. Step one, right? What is step one? The creation of our electrophile, yes? Right? So we're gonna have the creation of our electrophile, H2SO4, right? And that should give us what? Nitrous acid, so then call it. Alright. Plus our hydrogen sulfate, right? Because it's lost a hydrogen there. And what we're going to end up with now is this positive substituent. Let me put the 3 there plus that, right? And it will give us NO2, the nitronium ion. That is what we're interested, plus H2O, right? Quick reaction, right? No problem at all, right? What happens now is that the nitrobenzene, let me just add this like that. We already have nitrobenzene, right? What's going to happen is that the nitronium ion is going to be adding now. So the electrons are going to be moving on to our electrophile. Look at that. Look at that neatly, right? And what we're going to end up with now is an intermediate, NO2, right? We're going to end up with a positive charge there because we break the bond, right? And we break aromaticity. Can anybody tell me what is happening? Why we break aromaticity? How we break it? In relation to the hybridization of the carbon, how we break aromaticity? What is Huckel's principle and what did we break? Ah boy. Are we lost?
Yes, sir. What is it supposed to be again?
So we know that the carbon here is sp2 hybridized and Huckel's principle states. Let me go straight back to the beginning now. Because I don't want anybody tell me that it wasn't there. Huckel's principle states that they have one p orbital on each atom of the ring. All atoms, all carbon atoms must be sp2 hybridized, right? So when we add the electrophile, it breaks that rule, right? And the carbon here is sp3 hybridized, breaking aromaticity, and that is why the ring is destabilized. Everybody understand? Hybridization, hybridization. And this is because it's not no longer planar. Because we know when it's sp2 hybridized, it's planar. When it's sp3 hybridized, it is tetrahedral in nature. Right? This is why I told you guys to go over geometry and resonance. All right, so this is what's happening now. The only way to restore stability to this molecule is to have deprotonation. Right? Deprotonation speaks to the fact that the hydrogen will be leaving. So we have the H2SO4 negative, right? We're gonna have the electrons attracting the hydrogen there, and then this bond will break heterolytically, donating its electrons back to the ring, creating a new stabilized molecule. The person who asked me to go through the steps, you seeing it?
Yes, sir. Thank you.
Make sense? All right, lovely. Okay, so let's move on now. It's the same thing for the bromination, right? Or any type of halogenation. The NO2 group is a meta directing group, or we can call it a 4 directing. I always, no, it can't be a 4 directing. You guys don't see me chat foolishness. It's a 3 directing group. All right, so that is that. So the meta will always be our primary product. Everybody good so far? Drop a 1 in the chat if we're ready to move on. Okay, Victoria said it. I didn't see the chat. Victoria did tell us that they moved from sp2 to sp3 hybridized carbons. All right. Okay, let's move on now. So the reduction of nitrobenzene. No, you don't need to know the mechanism for this, but you need to know the production of alanine, right? So the nitrobenzene now, in the presence of an acid such as hydrochloric acid, and within the presence of a strong reducing agent such as the metal tin, right? We can have the reduction of the nitrile of the nitronium group, right, to produce our amino group, right, our amine group. What is reduction? Somebody tell me what is reduction. What is reduction? Quickly. If you don't tell me what is reduction now, I'm going to end the meeting right here and we'll go yard. Okay, continue if you don't know what reduction is. Go ahead.
Third reduction is the gain of electrons.
Gain of electrons, right? What is reduction in the case of hydrogen?
Reduction is the loss of hydrogen.
Interesting. Do we all agree with that? Reduction is the loss of hydrogen?
Reduction?
Yes.
Um, I think
No,
it's a game.
reduction is the
Gain of
gain of
hydrogen.
hydrogen.
Lovely. And what is reduction in terms of oxygen? Reduction in terms
That
of
is
oxygen?
oxygen.
That is the loss of oxygen. Okay, lovely. Right? So what's happening here?
Losing oxygen and gaining hydrogen, so it's reducing.
Lovely. The reduction of nitrobenzene. So the oxygens are lost to the solution, to straight to the protons for the creation of water, right? And we end up with an amino group on the on the benzene, right? So when we have a nitro group, it is nitrobenzene. When we have an amino group, it is aminobenzene, or what we call aniline. You'll almost never see aminobenzene, so please learn the name aniline. Aniline is important for the creation of our dyes. So everybody likes to wear pretty clothes with all different types of colors, right? Your phenols and your dyes, right, interact with alanine in different types of complex ways to give you your brilliant colors, right? I'm going to talk about it, right? We are going to talk about it. Okay, so aniline is created in the presence of tin and hydrochloric acid at glacial temperatures, right? So I think the temperature should be around below 5. All right, I think it's around below 5 degrees Celsius at glacial temperatures, right? Glacial, it should be cold. All right. So nitrobenzene is reduced to phenylamine, right? Sorry, it should be phenylamine. It's not amine. It's not aminobenzene, right? That's an old name for it, but it's phenylamine, right? So let me write it: phenylamine, phenylamine, right? Or what we call aniline, right? So it's a mixture, right, of tin and concentrated hydrochloric acid that gives us this, right? It must always be in the presence of a base as well. So NaOH is important, right, for the creation and the liberation of the product, right? So we have that. So the sodium hydroxide is important for the liberation of phenylamine from a tin complex, right? Because it's not necessary for us to see the mechanism. I'm not going to draw the tin complex and see how sodium hydroxide releases the phenylamine from the tin complex. We don't need that. All we need to know, we have concentrated acid in excess sodium hydroxide, and we have tin, and nitrobenzene is reduced to aniline. That's all we need to know. Everybody good?
Yes, sir.
Yes,
It's
sir.
a lot to know, but make sure it's all good. All right. So pause here now. Just a little recap. So when methylbenzene reacts with electrophilic agents, the products formed are 2,4 isomers of methyl nitrobenzene. All right. When the methyl group of methylbenzene, all right, well, the methyl group of methylbenzene is 2,4 directing because it tends to release electrons to the benzene ring to stabilize their intermediates when it's at the 2 or 4 position. Nitrobenzene is reduced to phenylamine by reaction with tin and concentrated hydrochloric acid. So just some little tips there. So are there any questions? Go ahead. Go ahead. Go ahead. Go ahead.
Oh, sir. Yeah. So does the directing thing mean that whenever the methylbenzene reacts with something, those groups would end up going to the 2,4? Is what I mean by 2,4 directing.
That is exactly what it means.
Yes.
Lovely. Brilliant. All right. Okay. All right. All right. All right. It's lovely to see that I'm surrounded by geniuses. All right. So this is what we're having here now. Now we're getting into something interesting now. Now. Don't be me now. I want you guys to answer my question. Methylbenzene, commonly called toluene, is a derivative of benzene in which one of the hydrogen atoms of the ring system has been replaced by a methyl group. Number one, or the only question here, describe the reactions of methylbenzene with the following: bromine in the presence of a Friedel-Crafts catalyst, and a mixture of concentrated nitric acid and concentrated sulfuric acid. So to describe, right, means that you will not write the mechanism. If you write the mechanism, I will not care about how much marks you get. I'll just give you 0 because you did not read the question, right? It didn't ask for anything mechanistic, right? Some persons tend to jump to mechanisms each time them see a question. Don't jump to mechanism. The question never asks for you, you don't write any mechanism. It's said to describe it. So what you're going to be doing is writing our equation using structural formulae to see exactly what the problem is, right? So A, what would be the product of A? Somebody said more A would be. Go ahead.
Sir, 2 bromomethylbenzene and 4 bromomethylbenzene.
So you have 2 bromo and 4 bromo benzene. You can have those, right? But the full substituted product, what is it called? The full substituted product, what is it called?
Oh, 2,4
Six
dibromomethyl. Yeah, 2,4,6
tri
tribromomethyl.
bromoben. Okay, tribromomethyl. Lovely. And for B, a mixture of concentrated nitric acid and concentrated sulfuric acid. What is that calling? What type of reaction is that called? Is it halogenation? What is it?
To nitration.
Nitration. Lovely. Right? And what isomers are going to be coming out?
You can have 3,5 dimethylbenzene. methylbenzene.
All right. So we can, okay, that is possible. Those are what you're saying. That is possible. But what are the major products? What are the major products that we'll see? One of the major products will be 2-nitromethylbenzene, and the next major product will be 4-nitromethylbenzene. That is because it is a 2,4 directing group, right? So when we're asked to describe the reactions, that we're talking about now. And notice that there's no meta position of bromine on the ring. So we're talking about these reactions. We're not asked to do the mechanism, but we're just describing them. All right. So if you guys want to have a go at that, have a go at that. Let's move on now. Phenols. What are phenols?
And phenol is a benzene ring with the hydroxyl on it.